transfer switch requires an overcurrent protective device, or OCPD, for the transformer feed into it. This is to protect the circuit from overloads and short circuits. The overcurrent protective device can be either a circuit breaker or a fuse. The neutral to ground, or NG, bond should take place at the main switch in the switchboard. This is because the neutral to ground bond is required to connect the neutral conductor to the ground conductor. The main switch is the main point of power entry into the building, and it is where the neutral to ground bond should be made. The transfer switch should be rated for the amperage and voltage of the transformer feed. The generator should be sized to provide enough power for all of the building's loads. The transfer switch should be installed in accordance with the manufacturer's instructions. To further clarify, firstly, the requirement for an overcurrent protection device at the transfer switch stems from fundamental electrical safety principles. The National Electrical Code, or NEC, mandates protection against overcurrents to prevent damage to equipment, reduce the risk of fire, and ensure personnel safety. When a transformer feeds a transfer switch, it effectively creates a new power source downstream. This new source, like any other, needs to be protected against fault currents and overloads. Without an overcurrent protective device, a fault on the load side of the transfer switch could draw excessive current, potentially damaging the transformer, the transfer switch itself, and the wiring in between. Secondly, the location of the neutral to ground bond is critical for establishing a safe and effective grounding system. A properly established neutral to ground bond provides a low impedance path for fault currents to return to the source, allowing the overcurrent protective device to trip and clear the fault. Bonding the neutral to ground at the main switchboard ensures that this low impedance path is established at the point where power enters the building. This arrangement minimizes the potential for voltage differences between the neutral and ground conductors, which can cause equipment malfunction and increase the risk of electric shock. Placing the neutral to ground bond at the transfer switch, rather than at the main switchboard, could create multiple neutral to ground paths, leading to circulating currents and potentially compromising the effectiveness of the grounding system. Consider these additional points. 1. Sizing the transfer switch appropriately is crucial for reliable operation. The transfer switch must be rated to handle the full load current of the transformer feed as well as the available fault current. Consult the manufacturer's specifications and relevant electrical codes to determine the correct size transfer switch for your application. 2. Proper generator sizing is essential for ensuring that the generator can adequately supply power to the building during an outage. Calculate the total load requirements of the building, including both essential and non-essential loads, and select the generator that has sufficient capacity to meet those needs. 3. Adherence to the manufacturer's installation instructions is paramount for ensuring the safe and proper operation of the transfer switch. The manufacturer's instructions will provide detailed guidance on wiring, grounding, and other critical installation procedures. Ignoring these instructions could result in improper operation, equipment damage, or even safety hazards. Furthermore, it is important to understand the concepts of separately derived systems and service equipment as they relate to grounding and bonding. A separately derived system is a power source such as a generator or transformer that has no direct electrical connection to the primary power source. In a separately derived system, a neutral to ground bond is typically required at the source. Service equipment, on the other hand, is the main point of power entry into a building and typically includes the main disconnect and overcurrent protection. In service equipment, the neutral to ground bond is also required. In your situation, the transformer is considered a separately derived system, and the main switchboard is considered the service equipment. Therefore, the neutral to ground bond should be located at the main switchboard, as it is the service equipment. The transfer switch, in this case, is simply a means of switching between the normal power source and the emergency power source, and it does not require a separate neutral to ground bond. To provide a more detailed explanation about the overcurrent protection requirements, firstly, it's essential to recognize that transformers are susceptible to both overload and short circuit conditions. Overload conditions occur when the transformer is supplying more current than it is designed to handle, leading to overheating and potential damage to the transformer windings. Short-circuit conditions, on the other hand, involve a direct connection between two or more conductors, resulting in a very high current flow. This high current can quickly damage the transformer, the wiring, and other equipment in the circuit. The overcurrent protective device at the transfer switch is designed to protect against both of these conditions. For overload protection, the overcurrent protective device should be sized to trip at a current level that is slightly above the transformer's rated current. This will allow the transformer to handle normal load fluctuations without tripping the overcurrent protective device, while still providing protection against sustained overloads. For short-circuit protection, the overcurrent protective device should be capable of interrupting the high fault current that can occur during a short-circuit condition. This requires the overcurrent protective device to have a sufficient interrupting rating, which is the maximum amount of current that it can safely interrupt. Secondly, the neutral to ground bonding location is critical for maintaining a stable and safe electrical system. The neutral conductor is the return path for current in a single-phase alternating current circuit. The ground conductor, on the other hand, is a safety conductor that is intended to provide a low impedance path for fault currents to return to the source. When the neutral and ground conductors are properly bonded together, they create a single reference point for voltage in the electrical system. This helps to minimize voltage differences between the neutral and ground conductors, which can cause equipment malfunction and increase the risk of electric shock. Bonding the neutral to ground at the main switchboard ensures that this single reference point is established at the point where power enters the building. This arrangement provides the most effective protection against electrical hazards. If the neutral to ground bond were located at the transfer switch, there would be two separate neutral to ground bonds in the system, one at the transformer and one at the transfer switch. This could create multiple neutral to ground paths, leading to circulating currents and potentially compromising the effectiveness of the grounding system. Thirdly, it is important to consider the specific requirements of the National Electrical Code, or NEC, when designing and installing electrical systems. The NEC provides detailed guidance on overcurrent protection, grounding, bonding, and other aspects of electrical safety. Consult the NEC and other relevant standards to ensure that your electrical system is safe and code compliant. For example, NEC Section 250.24 addresses grounding of service-supplied alternating current systems. This section specifies the requirements for bonding the neutral conductor to the grounding electrode system at the service equipment. NEC Section 445.13 provides requirements for overcurrent protection of generators. This section requires generators to be protected against overcurrents by an overcurrent protective device that is sized in accordance with the generator's rating. NEC Section 700 addresses emergency systems. This section provides requirements for the design, installation, and testing of emergency power systems, including generators and transfer switches. In summary, the transfer switch requires an overcurrent protective device for the transformer feed into it to protect against overloads and short circuits. The neutral to ground bond should be located at the main switchboard to provide a stable and safe electrical system. Consult the NEC and other relevant standards to ensure that your electrical system is safe and code compliant. To add further depth, let's delve into the specific types of overcurrent protective devices that can be used at the transfer switch. The two most common types of overcurrent protective devices are circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent condition is detected. They can be reset and reused after tripping, making them a convenient option for overload protection. Fuses, on the other hand, are single-use devices that melt and break the circuit when an overcurrent condition is detected. They provide reliable short-circuit protection, but they must be replaced after they blow. The choice between circuit breakers and fuses depends on the specific application and the level of protection required. Circuit breakers are generally preferred for overload protection, as they can be reset and reused. Fuses are often used for short-circuit protection, as they provide a high level of interrupting capability. It is also important to consider the interrupting rating of the overcurrent protective device. The interrupting rating is the maximum amount of current that the device can safely interrupt without being damaged. The interrupting rating must be high enough to handle the available fault current at the transfer switch. The available fault current is the amount of current that would flow during a short circuit condition. It can be calculated using a fault current study. In addition to overcurrent protection, it is also important to consider ground fault protection. Ground fault protection is designed to detect and interrupt ground faults, which are unintentional connections between a conductor and ground. Ground faults can be dangerous, as they can cause electric shock and fire. Ground fault protection is typically provided by a ground fault circuit interrupter, or GFCI. A GFCI is a device that monitors the current flowing in the circuit and trips if it detects an imbalance, indicating a ground fault. GFCIs are commonly used in residential and commercial applications to protect against electric shock hazards. Now, let's explore the different types of grounding electrode systems that can be used to ground the electrical system. The grounding electrode system is the connection to earth that provides a low impedance path for fault currents to return to the source. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. Ground rods are copper or copper-clad steel rods that are driven into the ground. They are a common type of grounding electrode and are relatively easy to install. Ground plates are metal plates that are buried in the ground. They provide a larger contact area with the earth than ground rods, making them more effective in areas with poor soil conductivity. Metal water pipes can also be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet. The grounding electrode system must be properly sized to handle the available fault current. The size of the grounding electrode system is determined by the size of the service entrance conductors. The NEC provides detailed requirements for grounding electrode systems in section 250. In addition to the grounding electrode system, it is also important to consider the bonding requirements for the electrical system. Bonding is the process of connecting all of the metal parts of the electrical system together to create a low impedance path for fault currents. Bonding helps to minimize voltage differences between the metal parts of the electrical system, which can reduce the risk of electric shock. The NEC provides detailed requirements for bonding in section 250. In summary, overcurrent protection, ground fault protection, grounding, and bonding are all essential components of a safe and reliable electrical system. Consult the NEC and other relevant standards to ensure that your electrical system is properly designed and installed. Let us further refine the concepts around neutral to ground bonding specifically. The purpose of the neutral to ground bond is to establish a reference point for voltage in the electrical system. Without a neutral to ground bond, the voltage on the neutral conductor could fluctuate, which could cause equipment malfunction and increase the risk of electric shock. The neutral to ground bond also provides a low impedance path for fault currents to return to the source. This allows the overcurrent protective device to trip and clear the fault, preventing damage to equipment and reducing the risk of fire. As mentioned earlier, the neutral to ground bond should be located at the main switchboard, as it is the service equipment. This arrangement provides the most effective protection against electrical hazards. If the neutral to ground bond were located at the transfer switch, there would be two separate neutral to ground bonds in the system, one at the transformer and one at the transfer switch. This could create multiple neutral to ground paths, leading to circulating currents and potentially compromising the effectiveness of the grounding system. It is also important to understand the difference between the neutral conductor and the grounding conductor. The neutral conductor is the return path for current in a single-phase alternating current circuit. The grounding conductor, on the other hand, is a safety conductor that is intended to provide a low impedance path for fault currents to return to the source. The neutral conductor is typically insulated, while the grounding conductor is typically bare. The neutral conductor is connected to the neutral point of the transformer, while the grounding conductor is connected to the grounding electrode system. The neutral conductor and the grounding conductor are bonded together at the main switchboard. In addition to the neutral to ground bond, it is also important to consider the equipment grounding requirements. Equipment grounding is the process of connecting all of the metal parts of the electrical equipment to the grounding system. This helps to minimize voltage differences between the metal parts of the equipment, which can reduce the risk of electric shock. The NEC provides detailed requirements for equipment grounding in Section 250. In summary, the neutral to ground bond is a critical component of a safe and reliable electrical system. It establishes a reference point for voltage, provides a low impedance path for fault currents, and helps to prevent electric shock. The neutral to ground bond should be located at the main switchboard, as it is the service equipment. Furthermore, let's address some common misconceptions about transfer switches and grounding. One common misconception is that the transfer switch itself needs to be grounded. While the metal enclosure of the transfer switch should be bonded to the grounding system, the transfer switch itself does not need to be grounded. The grounding system is connected to the grounding electrode system, which provides a connection to earth. The transfer switch simply switches between the normal power source and the emergency power source. Another common misconception is that a 4-pole transfer switch eliminates the need for a neutral to ground bond. A 4-pole transfer switch switches all 4 conductors, including the neutral conductor between the normal power source and the emergency power source. However, the neutral to ground bond is still required at the main switchboard, as it is the service equipment. A 4-pole transfer switch simply isolates the neutral conductor from the normal power source when the generator is running. Another common misconception is that the generator needs to be grounded separately. The generator should be connected to the grounding system, but it does not need to be grounded separately. The grounding system is connected to the grounding electrode system, which provides a connection to earth. The generator is simply another piece of electrical equipment that is connected to the grounding system. It is important to consult the NEC and other relevant standards to ensure that your electrical system is properly designed and installed. A qualified electrician can help you to determine the specific requirements for your application. Also, remember that proper documentation is crucial for maintaining a safe and reliable electrical system. Keep accurate records of all electrical work, including the location of the neutral to ground bond, the size of the overcurrent protective devices, and a grounding system configuration. This documentation will be helpful for troubleshooting problems and performing maintenance. In closing, understanding the principles of overcurrent protection and grounding is essential for ensuring the safety and reliability of your electrical system. By following the recommendations outlined in this guide and consulting with a qualified electrician, you can create a safe and code-compliant electrical system.